Dude, they would have gobbled that up. They would have loved that.
I know. Well, I just didn't. The timing didn't work out. So anyway, just wait. I'll do my YouTube. Okay. So anyway, so there's related rates. Okay, you viewers can read this on your own. Pause the video and read it. All right. No, I'm just kidding.
That's funny.
Okay. So let's start an example. Let's look at an example.
I just want to get the notes up.
As an example, wow, handwriting.
Yeah.
What is that? As an example, let's consider. Well, let me say one thing is that this desk is like slightly bumpy. There's like teeny little bumps in it, and so when I write, it like just kind of like.
It's like when you're ice skating on a rink that's not been like covered recently, and then you're like,
Yeah, so you just need to get a Zamboni and drive it over your desk.
Yeah, I need a desk Zamboni.
A Zamboni. Zam.
Sam Desconi.
Sounds like a really intricate Italian dish.
That's right.
Oh yeah, let me get the Zam.
The Sam Desconi is delicious.
Oh God, I need something to drink. So my notes are getting bad.
this is gonna make an alien.
There's a balloon, and it's being inflated. It looks already inflated, but it's being inflated. Okay, just pretend. There's a tube or something like that. All right. What shape does a balloon roughly resemble?
Square.
Oh, well, so three-dimensionally, a sphere, right? A sphere. So, volume for a sphere, anybody?
4/3 pi.
4/3 pi r cubed.
Okay. Good thing you all know that.
Christian's like, good job, guys.
So that's the formula that kind of, would relate some pieces of information here about the balloon, right? And let's think about the rates of change of the balloon here. So for example, if I wanted to talk about the rate of change of the volume, okay, and in general for these related rate problems, we're going to be doing these with respect to time because, as time goes on, things will be changing. So these are all going to be with respect to time. So we'll call that then dV dt, the rate of change of the volume with respect to time. As the balloon is being inflated, what we expect is going to happen to dV dt? It's going to be, the volume will be increasing, and so we would expect then for dV dt to be positive. The rate of change, if the rate of change is positive, that means the volume should be increasing. Okay. What about the rate of change of the surface area? I'm just going to abbreviate that as SA. What about the rate of change of the surface area of the balloon? It's going to be increasing as well, so we could say that like D, and I guess I'll just use like a capital S, not the SA, but just the rate of change of the surface area with respect to time, we'll say is also then going to be positive because the surface area should be increasing. Okay, right, unless your balloon plops and the surface area goes away. So does the volume, away. And lastly, what about the rate, I'm just going to abbreviate rate of change here too, the rate of change of the radius then. What do we kind of expect, how do we expect that to be changing as we inflate the balloon? It will also be, the radius will be increasing, and so therefore the rate of change of the radius we'd expect to be positive. dr dt for the radius. R.
They come out of ink, or very close to it.
Oh, that stinks. I hate when that happens. Okay, so that's kind of like the general gist. Today, we're not going to worry too much about doing any sort of like word problems. We're just going to make sure we can get down the very basics of related rate problems. So tomorrow we'll start with the word problems, which everyone loves, word problems. All right. But that's the kind of the gist of it, okay? So, let's start into an example of what we're going to be responsible for today. So let's suppose x and y are both differentiable functions of t. So x is a function of t. Again, t, we're talking about time basically here. Whoops, not period. So suppose x and y are both differentiable functions of t and, bless you, are related by the equation y equals x squared plus 3. So x is some function that's related to t. So x is changing with time, y is changing with time. All right, and then both x and y are related by y equals x squared plus 3. All right. Our goal then is to find dy dt when x equals 1, given that dx dt is 2 when x is equal to 1. Okay, so a lot of things are happening here, so let's give you a chance to write this all down, and then we'll kind of marinate on this a little bit. That's right. Yeah, Donna. Yeah, you can put a comma there. I accidentally put a period, and that was not the end of my sentence, so if you want to make it a comma, that'll work.
Wow, you can see something fantastic.
Okay, so what's the thing we're trying to find here? Okay, so yeah, the key thing is recognizing that we want to solve for dy dt. There's a lot of pieces of information in here. We're solving for dy dt. All right. We have this equation here that relates x and y. All right, but we want to find dy dt. So for this equation, if I want to find a dy dt, what does that mean I need to do to this equation? Take the derivative with respect to t. Right. I'm not interested in dy dx here, so I'm not going to take the derivative of both sides with respect to x. I'm taking the derivative with respect to t. Now, you look at this equation. Are there any t's in this equation? No. So when we take this derivative, it's going to be like when we do that implicit differentiation, right? We're going to be taking the derivative of these with respect to t. So let's do that. So let's just take the derivative with respect to t. We have to, because we want to find dy dt. So we have to take the derivative with respect to t. Okay? So let's see here. So I'll do, and I'm going to make this very kind of explicit so you can kind of see. Explicit in the obvious way, not explicit in the bad word kind of way. I always wonder why. I think I'm using that in the right way, but anyway. Okay. So I'm going to take the derivative of both sides with respect to t. Derivative of y with respect to t, derivative of x squared plus 3 with respect to t. Okay, so how do we denote the derivative of y with respect to t? What is that? Yeah, it's dy dt. Okay, if this were like y squared, so it's not y, if this were like y squared, the derivative of that with respect to t, so I'll just do that over here on the side. So for example, if it was like y squared, okay, the derivative with respect to t of y squared, it would be 2y then times dy dt, right? Using that chain rule kind of idea there. Okay, but that's not what we're doing here. Now let's look at this. We want to take the derivative of x squared with respect to t. So what would that end up being?
2x.
Yeah, 2x, that's right.
Yeah.
dx dt. Again, because we're not taking the derivative with respect to x, we're taking it with respect to t, so the dx dt is there. And then what's the derivative of 3 with respect to t? 0, that's right. Okay, so now you can see where that word related rates comes in. We have rates. Okay, the rates with respect to time, and there's dy dt. So these are how these two rates are related. Dy dt, the rate of change of y with respect to time, is 2 times x times the rate of change of x with respect to t. So they're related. They're equal to each other in a relationship. All right, so that's step 1. Step 2, we want to find dy dt, and so we're going to plug in the given values for the variables. All right, so let's see here. Dy dt, that's what I'm solving for, so I'm going to leave that. Is there anything I can plug in for x?
1.
Yeah, so it's 1. Why do we want to plug in 1? Well, it says we want to find dy dt when x equals 1. So we'll plug in 1 for x. And then what's dx dt?
2.
Yeah, so when x is 1, the rate of change of x at that instant, right, so we need that piece of information. At the instant when x is 1, the rate of change is 2. So it's times then 2. And so the answer is 4. dy dt is 4 in this situation. So the rate of change of y with respect to time is 4. Obviously, there's no context here, so we can't really include units or anything like that. Later on, when we're in a context of like a balloon, or like an ice cube that's melting, or like a ladder sliding down a wall, or a rocket shooting up into the sky, different things that we'll see. We'll have context, we'll have labels and units and stuff like that. But in this case, it's just very generic. So, Don? So a balloon, well, you can imagine here, instead of x's and y's, I've got v's and r's as my variable. So I would take the derivative of this. So the derivative of v with respect to time is dv dt. And then the derivative of 4/3 pi r cubed with respect to time, well, the 3 would go out front, right? So 3 times 4/3 is just 4 pi r squared, right, times dr over dt. And so here's the relationship between the rates there. Okay? And then, of course, you need a scenario. You'd have information like, what's the rate of change of the volume of the balloon when its radius is 3 and its radius is increasing at a rate of 10 inches per minute or something like that. You understand? So something like that. Question, Connor? So in related rates, generally speaking, we're going to be taking the derivative with respect to time, yes. I'm trying to think. I'm pretty sure it's always going to be with respect to time, yeah. Because again, these rates, the idea is we're always trying to find the change in the lengths or the change in the angles with respect to time, because things are happening kind of over time. So yeah, and generally you can expect it to be with respect to time. All right, questions on any other questions on that? Good questions there, good questions. Thank you for those. All right, I'm going to have you guys try one then. I think you can. You can do it. That's right. Okay, so you guys try. I want you to find dy dt when x is 2, given that dx dt is equal to -1/2 when x equals 2. And x squared times y equals 12. And though that relates the x's and y. Relates. Okay, let me see. Do I have them? God bless. bless your heart. Yes.
Show like the very bottom of the last page. No.
Yes, somewhere here.
I know I have it, but I forgot to put where step 2 was.
No, I'm running out of things.
Oh, so I just put up 3 there.
You're welcome. So our first step, right, should be to take the derivative. I know you guys aren't quite done yet, but I'm... When we go to take the derivative here, what do we have to use? Product rule. Yeah, we got to watch that product rule. It's there. Right? It's x squared times y. So when we take the derivative of x squared times y, it's product. There's the first thing, there's the second thing. So it's the first times the derivative of the second plus the second times the derivative of the first, and then equals 0. Okay, good? Questions on that? It's against the first x squared times the derivative of y with respect to t dy dt, and it's y times the derivative of x squared. The derivative of x squared is 2x times the derivative of what's inside with respect to t, so dx dt. All right, now what should we do?
Plug in values.
Plug in the numbers. So let's see, what can we plug in for x? 2. What can we plug in for dy dt? That's what we're solving for, right? So we can leave that. And what can we plug in for y? Oh, okay. We don't have a y value, do we? Well, let's hold off on that. Let's see, 2x, so 2 times 2. And then what can you plug in for dx dt?
Negative.
Yeah, when x is 2, the rate of change at that instant is, negative 1/2, and then equals 0. Now, if I have dy dt and y, will I be able to solve for dy dt if I have dy dt and y in here? I have 2 different variables, don't I? If I have a y here and dy dt, so I got to figure out, I'm trying to solve for dy dt, so somehow I have to figure out what y is. Brittany, you want to say something?
Right, but you just like plug into this, if x equals 2, so maybe I was saying like 2 squared times y equals 12.
Yeah, that's right. We have this relationship over here that says x squared times y equals 12. If I'm trying to figure out what y is when x is 2, I can plug 2 in for my x. So I get 4y equals 12, which means that y is 3 when x is 2. So instead of leaving that y blank, we can say, aha,
Gotcha.
must be 3. And that's exactly what we have to do here. So another thing I'm trying to point out here is that sometimes in these related rate problems, we'll have some secondary work we sometimes have to do to be able to fill in all of our parts. But now that we've got the derivative taken successfully, we've plugged in for every other value except for dy dt, now we can finally simplify this. Okay, so we get 4 dy dt, and let's see here, 3 times 2 is 6, times 2 is 12, times negative 1/2 is negative 6. Okay, and so we get 4 dy dt equals 6, and so then dy dt equals 3/2. Again, no units, no labels, because we don't have a context here. It's just this.
So if we did like, we wrote down 3 over y, or y over 2, would we get like partial credit?
You'd probably get partial credit still, yeah. But the idea is, yeah, you want to come up with the actual numbers. So. Yes?
How do you know you could put 2 into the other equation like y?
Well, because we're told this equation relates x and y. And so if we're specifically trying to figure out, so in this, when we did this rate here, okay, we were trying to find the dy dt when x is 2. So at the instant when x is 2, we want to find dy dt. So when I plug in, okay, I also know that dx dt is negative 1/2. So all those things I can plug in for. Anytime I see an x, I'll plug in 2. Anytime I see a dx dt, I'm going to plug in negative 1/2 because those at the instant when x is 2, my rate of change of x with respect to t is negative 1/2. But again, it's like I need to figure out what y is. Well, again, if I want to know what y is when x is 2, if I want to find dy dt when x is 2, I need to know what y is when x is 2, and so I just use this equation that relates the x and the y. When x is 2, then this y will now give me the y value there. Okay, must. All right, so, yep, I'm going to do it. All right, we're going to look, I'm going to go then over some guidelines, and we're going to do one, like, legitimate related rate problem, okay? Those were kind of like baby food, baby steps, and now we're going to try some more legitimate one, Okay, so yeah, we're going to upgrade. No more pureed peas or anything like that, okay? So, guidelines for related rates. And bear with me here, there's a little bit of writing involved. And I know it's math class, but here we go. So I'm going to abbreviate here. ID, that's short for identify, right? ID all given quantities and all quantities. I'm gonna abbreviate again. TBD. You know what that stands for? To be determined. Okay, so identify all given quantities and all quantities to be determined. The ones you're going to be, solving for. A sketch with labeling is helpful. I'll put that in parentheses. A sketch with labels is helpful. Okay. Step 2. Write, once you've identified all the given quantities and all the quantities you want to determine, write an equation relating the variables. Sometimes you'll be given the equation that relates the variables, right? In the last 2 examples, we were given those equations. In the balloon example, all right, if I'm trying to find like the rate of change of the volume of the balloon, we can say, well, a balloon is roughly a sphere, and so therefore if I'm trying to find the rate of change of the volume of the sphere, I need to come up with a volume formula for the sphere. Okay, we're going to use a lot of like geometric volumes, or volume formulas, some area formulas and stuff like that too. Okay. Once you have an equation relating the variables, what should we do with that equation?
Differentiate.
Take the derivative. Yeah, so I'm going to use, differentiate both sides of 2. I'm just going to use the number 2 with a circle around it to, refer to the equation we were talking about with respect to what variable? Yep, with respect to t. And then step 4, plug in given values, solve for the required rate of change, whichever, one was asked. Solve for the required rate of change. And that's it, guys. It's as easy as 1, 2, 3, 4. Okay? It's that easy.
Easy as 1, 2, 3, square root of secant 4.
So we'll do an actual example here.
Delta 3.
Questions on any of those steps? You can kind of see that we did those things in a more like, I only showed 2 steps in the previous problems, I guess, but all the quantities and quantities to be determined were kind of given to us in the problem, so that was kind of like that was step 1. Step 2, then writing the equation, well, that was again already given to us. So really, in the previous problems, we were really just doing step 3 and step 4. If that works for you, Brittany, absolutely. If you need to do step 1 and 2, though, feel free to just throw those in there. All right, so let's try this one. A pebble is dropped into a calm pond.
Why doesn't this be calm? All right, Bob Ross.
Yeah, right? Happy little pond. Just beat the devil out of your brush. All right.
Titanium one.
That's right. Well, there's some Van Dyke Brown here. Okay. So anyway, a pebble is dropped into a calm pond, causing ripples. Happy little ripples.
Waves okay?
Sure. In the form of concentric circles.
Ooh,
You don't like the word concentric?
no.
Do you know what the word concentric means?
Circles
All right.
inside of each other.
So yes, so it's like literally the definition of the word is in the word. So we know con means with, right? And centric, center. So they have the circles with the same center, with the center. They all have the same center. So it's like circles within circles within circles kind of thing, right? This is what happens when you like throw a pebble into a calm pond. Like you have these like ripples that all have the same center where you threw that pebble in. Okay? The radius r of the outer ripple is increasing at a rate of 1 foot per second. That's right, we're using those standard measurements. Sorry, physics folks. When the radius is 4 feet, at what rate is the total area of the water, area A? So at what rate is the total area A of the disturbed water changing? Total area A of the disturbed water changing. Well, I was like, let's do it. Let's go crazy. Okay.
I need to sharpen my
If you want to hop up and do it real quick.
I'm gonna stick to it. So I couldn't
Okay,
do that.
sorry.
That like makes me cringe. It should be on our cringe-worthy pencils. That like.
So a pebble is dropped. So let's think about this. Okay, so a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Obviously, those ripples they're going to go out, right? The radius r of the outer ripple is increasing at a rate of 1 foot per second. So at a particular instant, I guess, the radius is increasing at a rate of 1 foot per second. Okay. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So obviously, what's happening to the area of the water? That's being disturbed. It's increasing, right? Because they're going out, so more and more water is being disturbed, right? So we want to figure out what is the rate of change of that total area that's being disturbed, okay, or the rate of change of the area that's being disturbed. So, what kind of formula should we use here, right? Our first step is to, our first step is to identify all given quantities and all quantities to be determined. So we have, let's see here, we have a radius, r is increasing at a rate of 1 foot per second. So is this r equals 1?
No.
How would I label it?
R equals 4.
Okay, so the radius is 4, so R is 4 feet, then what's this number 1?
The rate is 1 foot.
The rate is 1 foot, the rate of change of the radius. So how do I denote the rate of change of the radius?
Delta R.
Or dr dt in our case. The rate of change of r with respect to time. So it's going to be 1 foot per second. Okay, so that's another given piece of information. Is there any other quantity that we are given or quantity to be determined?
The area of the circle.
Yeah, our question is, what is the rate, at what rate is the total area A changing? So that means we want to solve for what? dA dt, the rate of change of the area. That's our question mark. So what formula can we use that relates area and radius? So yeah, the area of a circle, right? We're talking about a circle. These are concentric circles. So the area is equal to pi r squared. That is our equation. So there is step 1. Here's step 2. We wrote an equation relating the variables. Notice what I am not going to do here. I am not going to plug in 4 and then take the derivative. Okay? You don't start plugging in until after you differentiate. So that means step 3, let's differentiate this thing on both sides with respect to t. So the derivative of a with respect to t? dA dt. The derivative of pi r squared with respect to time? 2 pi r dr dt. Right, don't forget we're differentiating with respect to time. Okay, so there's the related rates, right? We see have some rates here, and they're related by an equation. And then last step, step 4. And again, you guys, like when you're doing the work here, you don't have to like put the numbers there, 1, 2, 3, 4. I'm just writing it very explicitly, so you can kind of like just have, aha, there's 1, it matches to that. There's 2, it matches to that. 3, 4. All right, now we plug in their numbers. So let's see, dA dt, that's what we're solving for here, so I'm going to leave that. And then 2, and then pi, those are still going to be there. What's our r? Our r. Okay. And what's dr dt?
1.
1.
Do we have to solve that one with the unit?
We'll put units at the end. So we'll multiply here. So 1 times 4 is 4. 4 times 2 is 8. So I'm going to go ahead and just call this 8 pi, so I can have it nice and neat and not have to worry about this nasty decimals or anything like that. 8 pi, and then what would the units be here? So right, go back to what we're trying to find. We're finding the change in the area. Area requires square units, right? Well, the only thing I have here are feet. So it's going to be feet squared per time, so per second. Okay, and if that's uncomfortable for you, like evaluating that based off of just looking at the rate, area is going to be in a square unit, so it's feet squared, and then per time, seconds. You can also look back up here in the original calculations. Did 2 have a label with it? Did this 2 have a label with it? Did this pi have a label with it? Did the 4 have a label with it? Yeah, it's feet. And what is this 1's label? Feet per second. So I took feet times feet per second, and that yields the feet squared per second units. Okay, another way to think about it. And that's our answer. 8 pi feet squared per second. Yeah, I'm okay with you leaving it as 8 pi. If it says to like round to 3 decimal places, feel free to do that, but you can leave it as 8 pi for sure. Okay. Questions on any of that? That's our introduction to related rates.